So hello everybody, welcome to this seminar. The presentation of today deals with guaranteed nonlinear model predictive control based on validated simulation. It will be given by Dr. Mohamed Fnadi. Mohamed is an associate professor with the Université du Littoral Côte in France, in the north of France, since September 2021. He received a master's degree and a PhD in robotics in 2016 and 2019, respectively. He held an assistant professor position at Sorbonne University from September 19 to June 20, and a postdoctoral fellowship with INSTA Paris from June 20 to August 21. His main research interests focus on control-based model, trajectory planning, interval analysis methods, and computer vision with applications to all terrain autonomous vehicles. So, Mohamed, you can start if you are ready.
Okay, thank you very much, Tariq, for this kind presentation. So I am happy to introduce some work that I did during my postdoc at INSTA Paris with Julien Alexandre Desandreto, associate professor at INSTA Paris, and Laurent Fribord, research director at ENS Paris-Saclay. So my talk today deals with the development of a new guaranteed nonlinear model predictive control via validated simulation. So in the first time, I will just start by a small introduction to make you in the context of this presentation. So control of robotic devices requires a very high accurate and stable controllers in order to ensure their stability and their safety during the executed task for which they are designed. And also they need a strong guarantees to be robust to different uncertainties. On the other hand, the control of these robotic devices is often designed using a mathematical or a physical model represented by the kinematic or the dynamic models, which are more specifically represented or formulated by the ordinary differential equations that depends on some uncertain and unknown parameters that necessitate to be identified in a guaranteed way. So the purpose of my talk today is about this point. So in the first research topic, so we have to estimate this dynamic models in a guaranteed way. When I say guaranteed way, it means that all the parameters must be estimated as intervals, taking into account different uncertainties coming from the system design, as well as the data sensors. And since all these parameters are identified, the second topic is to develop a new reliable and constrained NMPC, taking into account different uncertainties and using the validated simulation and verified simulation methods. Okay, so in order to introduce different motivations of this presentation, I think this scheme diagram can be more meaningful and more presentable. So here we have different blocks. We have the trajectory planner, and we have the robotic devices that interacts with its environment. So these two blocks we will not treat them in this presentation, and we will focus mainly on these two blocks. So the first block is the identification and observation block. So the purpose of this block is to identify all the dynamic parameters of this robotic device in a guaranteed way, taking into account different errors and different noises coming from the system design, as well as the embedded sensors data. Since all these parameters are identified, we will focus on the second block. So the second block is the control block, which depends on the first on this block, in order to adjust all the dynamic parameters to get some accurate controllers. So this control will be synthesized using the validated methods and using the NMPC approach, the nonlinear modal predictive control strategy. This kind of strategy is normally defined as an optimization problem that minimizes some cost function and respect different constraints related mainly to the intrinsic and physical constraints of the system on the state and input variables. So this is the main topics that we will treat in this talk. So I'll just introduce quickly the robotic device. So system with two rotational joints. So the first joint is actuated by a DC motor. The purpose to control this brushless motor in order to stabilize the inverted pendulum in the upright position, taking into account different uncertainties coming mainly from so here we have two incremental encoders to measure the rotational angle of each joint. So this is the robotic device that we will use in the framework of this presentation to validate different algorithms that we will develop. My presentation is organized as following. So in the first part, I will present some results done concerning the guaranteed identification of the dynamic model based on the interval analysis methods, as well as the set-inversion tools. And based on this first part, we will develop the second part, in which we will design a new reliable NMPC approach based on validated simulation. And we will conclude this presentation by a conclusion and future works. Okay, let's start by the first part. So here, I will just remind you the dynamic model. So we have a simple system with two rotational joints. So the dynamic model or the inverse dynamic model can be written by these nonlinear ordinary differential equations that depends on these matrices. So we have the inertial matrix, we have the gravity forces, and we have B, which is the centrifugal and Coriolis matrix. Okay, so we have gamma. Gamma is the external torque vector that depends mainly on the actuator's torque. Since the second joint is passive, so we don't have any actuator torque. And the friction, the torque here depends mainly on the friction torque. So here we have used a simple model to characterize the friction by this relation, where the friction torque is proportional to the velocity of each joint, and with this coefficient of viscous friction parameter. So the purpose here is to identify all the read parameters that represent the inertial and geometric parameters, as well as the frictional parameters, to identify all these parameters in a guaranteed way. So we can simply write this nonlinear ordinary differential equation by this simple form. So where Ym is the output vector, and F is the inverse dynamic model with all the measurements variables, as well as the needed parameters to be identified. So the P is the parameters vector that we have to identify in a guaranteed way. So in the literature, we can find some deterministic methods that allow us to identify these parameters in a deterministic way. And one of these methods, so the classical or the traditional least square method, allows to identify these parameters in a deterministic way. So the principle of this method is very easy. So we apply some exciting trajectory to the robotic device, and then from these trajectories we can measure the rotational angle based on using the increment, and by applying some no-causal derivative features, we can measure at each time step the velocity and acceleration. And using the inverse dynamic model, we can construct this observability matrix. And then on the other hand, we can also compute from the velocity different torques at each iteration by this mechanical relationship. And the least square method, the principle of the least square method is to optimize the error between these two vectors. So we have the measurement vector, and we have the estimated vector using the inverse dynamic model in order to compute in a deterministic way all the parameters. So when I say deterministic way, it means that all the parameters are estimated as constant values. So nevertheless, this method cannot guarantee a high quality of the identification, since we don't have taken into account any uncertainties of the system related mainly on the measurements of the embedded sensors. That's why we have to identify these parameters in a guaranteed way, taking into account interval analysis method and set-inversion, using interval analysis method and set-inversion methods. So this is the purpose of this part. So is to compute all these parameters as intervals instead of real numbers, taking into account different uncertainties coming from the system and the embedded data sensors. So for that perspective, we will use the CVA algorithm. CVA means set-inversion via interval analysis. But all the uncertainties and errors are bounded with a known prior bounds. So I will just introduce the principle of CVA algorithm. So here we have two spaces. So we have the parameter space and we have the dataset space linked by this inclusion function that represent the inverse dynamic model. So we can distinguish three kinds of subhavings. So we have the feasible subhavings that belongs to the feasible set of parameters. And we have the unfeasible subhavings that mix an empty set with this feasible set of parameters. And their images is outside of the output box, and we have the undetermined one, the green ones, or what we call also the penumbra, that are not either inside or outside of these feasible parameters. And in this case, we have to bisect many times these subhavings until achieving the accuracy and the precision of the CVA algorithm. So in this case, we will compute the feasible parameters as intervals, taking into account that all the measurements are considered as intervals by adding a bounded error and by respecting this equation. So where this interval is the output interval, and from that we can compute at each measurement the tight interval of all these parameters. So the feasible and acceptable dynamic parameters can be computed by this form. So it's the reciprocal image of the output box intersected with the initial domain of the parameters. Okay, so now I will introduce some results then using these two methods. So here we have used the nonlinear inverted pendulum in order to estimate all the parameters in a guaranteed way. So we have applied two exciting trajectories. So this one is the first trajectory, and this figure depicts the second trajectory. So as we can notice that all the recorded data here are represented by intervals, by adding a bounded error to each collected data and each recorded data. So in the first time, we have applied the least square method to determine the parameters in a deterministic way. So this row is the results of the least square method using the first trajectory, and this row is the results of all the parameters using the second trajectory. On the other hand, we can use also the CAD software. So here we use SolidWorks to estimate mainly the inertial and geometric parameters, these 5 initial parameters. And we can notice that the deduced parameters are much close to the estimated ones using the least square method. In that perspective, so here we have, for these 5 initial parameters, we have computed the mean value of these three values. And from the mean value, we have quantified the error related to this first identification. And the results are summarized in this table. So here we have the geometric and the inertial parameters. We have the mean value of each parameter, and we have the uncertainty linked to in order to make these parameters into some intervals between the upper and the lower bounds. And using that, we have applied the CVA algorithm for each trajectory. So this one is the subhaving generated using the first exciting trajectory, and the second one is the subhaving generated using the second exciting trajectory. So from these two results, we have fixed the centered and the common box, which is limited by these 2 intervals. The first interval is the friction parameters of the first, the viscous friction parameters for the first joint, and the second one is the viscous friction parameters for the second joint. So in order to show the usefulness and the quality of our identification, so the first time we have applied the cross-validation method. which is very small. The idea is to compare the measured torque using the real system with the estimated ones, using the least square parameters and the CVA parameters. So we can notice that all the curves are close to each of them, which is a good thing. And we have computed the root mean square error to evaluate this result. So the root mean square is around 6% when we use the least square parameters, against 2% when we use the interval method, which indicates a good fit and a good coherence when the variable and uncertainties are accounted. Okay, on the other hand, to further evaluate our identification, so we will use the DynIbex library. So DynIbex library is a sophisticated solver of this kind of ODE, or initial value problem of nonlinear ordinary differential equations. So the dynamic model can be written in a forward form. So where x is the velocity, is the position and velocity of each joint, and p is the identified parameters. So we have some initial conditions. So here we have the initial condition of the input of the state variable that belongs to this interval, in order to take into account some uncertainties related to the initial condition. And we have also the input variable that belongs to this interval. So here we will assume that if is Lipschitz and continuous, in order to ensure that at each iteration we can get a unique solution of this ODE equation. So to solve this ODE equation, so as I said, we will use the DynIbex library, which is a sophisticated solver developed at Paris. The idea of DynIbex is very simple. So here the idea is to get the solution of the ODE. So we can at the first time we compute a sequence of time instants, and then we can compute a sequence of intervals of each state variable along the simulation time, and then we compute the tight enclosures by considering the time interval. So here we have intervals in time, and we have intervals in the state variable at each instant. So this is the main concept of the DynIbex library. So we have applied this DynIbex library in order to evaluate our identification, and we got these results. So here we start from this initial condition. Look, the pendulum arm is in the beginning is in this interval, and then the input variable is in this interval. So we did the guaranteed numerical integration, and we got these results using the least square parameters. So here the parameters are considered as constants, and we use also the CVA parameters when all the parameters are considered as intervals. And we use the real system. We measure under the same conditions and the same input, we measure the rotational angle of the pendulum arm. So we can notice that all the curves are very close, which is good enough to confirm that our identification is good. And to evaluate that, we can compute the coverage ratio that can be calculated by this equation. So where nt is the number of times when the measured time is included into the simulated interval time. If so, we compute the number of times if the corresponding measurement is included into the simulated state interval. So this coverage ratio is around 60% when we use the CVA parameters, against 30% when we use the constant values, which indicates that when we consider the uncertainties related to the parameters, we have a great coverage between the real system, or the physical reality of the system, with respect to the dynamic model. So we did this kind of guaranteed simulations under different initial conditions, and the results confirms the first results of the first simulation. Okay, so in this part, to summarize in this part, so we have identified the guaranteed parameter, the dynamic model in a guaranteed way. It means that all the parameters are identified as intervals. We did some guaranteed simulations to validate this guaranteed identification, And the conclusion is that when we identify the parameters in a guaranteed way, we increase the coverage ratio between the physical reality and the real system. So now we will we will apply this guaranteed identification in order to develop our new reliable and guaranteed nonlinear modal predictive control using the validated simulation method. So before that, I will just introduce the concept of modal predictive control. So the concept of modal predictive control, this kind of strategy is well used in automotive engineering as well as chemical processes due to many reasons. So first, its ability to handle system nonlinearities and also the multivariable system. Second, its ability to anticipate. So here we have the reference trajectory, so we can anticipate the change of the reference trajectory along the prediction horizon. And finally, the capability of this kind of strategy to handle constraints of the system that are critical and necessary for the safety and stability of the dynamic and critical systems. So the algorithm of NMPC, so at each time step, we compute the input variables along the prediction horizon. So this signal, the prediction horizon denoted NP, and from NP and the period of this input signal, we can compute the prediction time. So at each time step, we compute this vector. So this vector is the component of this signal. And then once this vector is computed, we inject into the system the first input in order to stabilize the system, the dynamic system, and we repeat this process until achieving the final point of the reference trajectory. Okay, so this kind of problem generally are formulated as an optimization problem, or more specifically as a quadratic programming problem that minimizes some cost function and respects different constraints related mainly to the input variables and state variables expressed as inequalities. So for the cost function, it can be written by this continuous integral along the prediction time of this quadratic form. So the quadratic form can be written as a function of the predicted output using the dynamic model and the reference trajectory or the reference set point. It takes into account also the norm of the input variables. So the idea is to minimize this cost function in order to compute the optimal input and safe input that must be injected into the system. Q and R are the Witten matrices that must be adjusted also adequately in order to ensure the convergence of the controller and the stability of the system. So this presentation is, we can see that it's a deterministic modal predictive control. Now we need to develop a guaranteed nonlinear modal control by integrating interval arithmetic. So for that, we will use the guaranteed numerical integration as I explained based on the range quota methods. So our dynamic model can our dynamic model can be written in the direct form or in the forward form by this ordinary differential equation. So the idea is to solve this ODE equation. So we can solve this ODE equation by classical and standard numerical integration based on the range quota schemes that is given by this recursive equations, where different coefficients are deduced by this Butcher tableau. And the idea is to solve this ODE in a guaranteed way and validated way. So when I say guaranteed way and validated way, it means that at each time step, we have to compute the state variable as interval by ensuring this inclusion, the image by the inclusion function of these parameters must be a subset of the new state variable as time tg plus 1. So this is the DynIbex libraries. We use DynIbex library to develop and to design our NMPC in a guaranteed way. So our validated NMPC global approach is based So the purpose of this validated NMPC is to compute the input variable along the prediction horizon as intervals. So we'll compute this box. We have the box of the input variable along the prediction horizon that is represented by this Cartesian product. So we have two steps, as can be seen by this pseudocode. So in the pseudocode as input, so we have the reference interval, the initial interval, and we have the NMPC parameters. So at each time step, we make some validated simulation to compute the new state interval. And then we have the first step is the filtering and branching that allows to compute the box of input variables along the prediction horizon in such a way state variable constraints are satisfied, and also ensuring the convergence to the reference interval. And the second step, we will apply, since this box is computed, we will apply some optimization, some interval optimization in order to compute the suboptimal input intervals that minimizes as much as possible a new formulated interval cost function. So now we will detail the first step, so the filtering and branching. So as I said, as inputs, so we have the initial condition interval, we have the set points interval, and we have the NMPC parameters, the prediction time, input sampling period, and the time and the prediction time. We have the final time of simulations, and we have the different constraints on the input and state represented by these intervals, the minimum bound and the maximum bound, and we initialize the control box by this interval vector. Okay, and then in the first time we apply the validated simulation using DynIbex library to solve the ODE equation, assuming that the input interval is known. So in the beginning, we take this interval limited by these bounds, and we make the valid simulation to compute the equivalent state intervals, and we check if this new state interval is included into the interval into the set point interval. If so, we repeat the valid simulation to compute the new input interval. If not, we have to bisect many times the input interval and restarts again the validated simulation to compute a new state intervals, and then we keep just one side, the left or the right side of this input interval by considering this criteria. So we eliminate the branch leading to unsafe state, and also we remove the parts that can generate state intervals which is far from the reference interval, and also we eliminate the one who can lead the system to the opposite ways. So the opposite ways, it means that the computed input interval can move the system in the forward and the backward direction, which is not suitable. So here we talk about the sensitivity analysis, and then we repeat this until achieving the prediction horizon. Okay, so since all this box is computed, so we launch the interval optimization part. So as I explained, the cost function can be calculated in a deterministic way by this integral of this quadratic form. Depends mainly on the predicted output and the reference trajectory and the norm of the input variable. We can use the linearity of the integral to reformulate this integral by this discretization. And since the input variables are constant along this step time, so we can write the second integral by this summation. And then we can bracket this integral in these intervals, and we can approximate this cost function by this upper bound of this interval. So the optimization algorithm can be formulated by this pseudocode. So the idea here, we have we have as input the reference interval, and we have the computed state intervals, and we have the computed input intervals given by the filtering and branching algorithm. And then we have some tolerance value of the first tolerance value of that represent the width of the first input interval, which is more important because this interval will be injected into the system. So the idea here is to make some dissections to minimize the size of the first interval in the left and right. We compute the cost function, and we keep the box that allows to minimize this cost, this interval cost function, and then we inject into the system the minimum bound of this feasible and acceptable interval inputs. So this solution is suboptimal, but it is robust to different uncertainties because it is based on interval arithmetic. So now I will just show you some results concerning the validated NMPC. So this is the different parameters that we have tuned in order to validate our guaranteed nonlinear model predictive control. So this is the different parameters of NMPC: the prediction horizon, the input sampling period, the prediction time, and the final time of simulation. We have different constraints on the state variables and actuator limits. And we have also the goal interval or the desired set point interval, which is the upright position, because we want to stabilize the pendulum arm is around P. So we have this interval as desired reference interval. And the Witten matrices, so we have the Witten matrices of the input variables and the Witten matrices for the state variables. So this is the results using the DynIbex library. So here we have started from this interval, so 149 degrees, 151 degrees, which is not far from the equilibrium point. And we did the validated simulation by NMPC approach to stabilize the pendulum arm in this upright position. So we can notice that all the intervals, so here we have enclosures. We can notice that all the enclosures of the pendulum arm converge to the reference a small settling time around 0.2 seconds. On the other hand, this figure depicts the DC motor torque, and we can notice that that in the beginning the DC motor is strong in order to help the pendulum arm to reach the equilibrium position, and then in the steady state domain, the torque changes sign in order to maintain this equilibrium position. We did also the validated simulation starting from another initial position around 0. It means that the pendulum arm in the beginning is in the downward position, and we can notice that validated NMPC succeeds to stabilize the pendulum arm in the upright position because all the computed enclosures converge to the reference interval. And the same thing, the torques here are maximum in the beginning in order to help the pendulum arm to reach this interval reference. And since the reference interval is reached, we alternate the sign of the torque in order to maintain and to keep this position. So the results are quite satisfactory. Nevertheless, the computation time is very high. So it's very high. So we could not validate this approach in real time using the real system. That's why we validate this approach offline by injecting these inputs into the real system, and we want to see what is the behavior of the real system, since the identification is quite in the physical reality of the system has the same behavior than the dynamic model. So we have injected these inputs into the system, and we got these results. So when we start from the position not far from the equilibrium point, we see that the pendulum arm succeeds to stabilize around P. However, when we start from the downward position, we didn't succeed due to some reasons that depends mainly on the synchronization problems between the between the real system and the simulation results under DynIbex. So we can see that, that the proposed validated NMPC is robust to different uncertainties, is safe because it allows to respect different constraints related on the state and input variables, and is suboptimal because it's based on the optimization, interval optimization. However, it requires a huge time computation that prevents us to validate it in real time. Okay, so now I will sum up. So in this presentation, we have discussed many research topics. So the first topic is the guaranteed identification, in which we have identified in a guaranteed way the dynamic model of a new nonlinear inverted pendulum based on interval analysis and set-inversion. The main contribution of this first part is the guaranteed numerical integration based on the real system in such a way to increase the coverage ratio between the real system and the simulated model. The second contribution, we have proposed here a new formulation of a new guaranteed nonlinear model predictive control based on validated and verified simulation, which is robust to different uncertainties and satisfies at each time step different constraints related to the system state and input variables. As the future works, so as I said, this guaranteed nonlinear model predictive control needs to be improved, mainly the real-time improvements, by using some efficient onboard GPU and also by using some distributed computing methods and relaxation methods in order to optimize our algorithms. On the other hand, we have to project all our algorithms on a complex system, mainly underwater robots or some mobile robots, and also development of some interval observers in order to estimate the environment and inject this estimation into the controllers to improve the accuracy of the guaranteed controllers. Before concluding, I will just talk a little bit quickly about our project INR that we have submitted this year. And so this project deals with the development of a new autonomous and innovative robotic device, an autonomous vehicle, to detect and locate different road defects. So here in this project, we will enlarge our NMPC, guaranteed NMPC, to perform some tasks mainly related to mainly to trajectory tracking and the estimation of the environment. So on the other hand, we will use in this project some 3D LiDAR sensors in order to perceive the environments and also to detect some road defects in real time. Okay, for more details, I recommend you to review these two articles that deals with this talk. Thank you very much for your attention.
Thank you, Mohamed, for this very nice presentation. So we have time for questions. Who would like to start? Who has some questions, please?
Maybe, I don't know if anyone. Okay, thank you for this very nice talk. So my first question, yes, I have one question. It's about when you define at the beginning the set of parameters which are feasible or not. So you say that it is maybe you have no number in your slides, so it was difficult for me to point you which slide it is. But it is among the previous one, at the beginning, when you define the set of all parameters up here. Yes. Such that there exists Q, there exists Q dot, and so on. But Q, Q dot, and Q dot dot are linked by some differential equation. One is a derivative of the others. So yes, maybe one point may belong to PI as you define it, and may not be feasible if you do not. Because Q dot and Q dot dot are linked all together. You understand what I mean?
Yes, yes.
So you define here a subset of the set of feasible parameters, maybe.
Yes, en fait, sorry. So in this part, what we did, so Q is the data coming from the incremental encoder. Yeah. This data is we add a bounded error to this data to make Q in this interval, and then from this signal we have applied, as I said here, we have applied a derivative filter, no causal derivative filter, to get the velocity, because we don't have the velocity sensor and we don't have the acceleration sensor. So we apply some derivative filter to compute the velocity and the acceleration. And from these computed values, we have added some uncertainties. We have added some errors to bracket each computed value in an interval.
Okay.
That's why we have these intervals here.
Yes, but they are linked.
Yes, they are linked by the derivative filter. Yes.
Yeah. Okay. Thank you. It was my only question. Okay. Thank you. Very nice talk. Thank you.
I had the same question as Luc. What kind of filter did you use here?
So first we have two in our experiments. We have two filters. We have one filter to eliminate the noise. It's a Chebyshev filter, discrete filter, and the second one we have synthesized this filter. We used some functions of MATLAB. I think FIRPM. I don't know what is the main. We give just
some kind of finite impulse response filter.
I think yes. I think it's réponse impulsionnelle finie filter. We have designed this kind of filter using MATLAB to get the parameters of the filter that to respect some gabarit, by respecting some.
Okay, maybe I have again a question exactly to this problem here that Luc and also Tarek mentioned, because when you're using such kind of filter, you may introduce some artificial delay phenomena. Mm-hmm. And I have two remarks how you could do better. One thing is, since you already performed your complete identification experiment, you have the complete horizon of data. That means you can do some kind of forward-backward filtering in order to eliminate phase shifts. Those zero phase filters that typically just work offline because you have to run through the data in backward direction. And since you already mentioned the MATLAB functions, I think in MATLAB you just have to use the filt command applied to your filter, and then you can eliminate at least phase shifts. That's one thing. The other thing maybe is still you may lose some part of the solution, because if you look at, I think it was, I wrote it on the slide 13. Because what puzzled me a little bit is that you don't have a coverage ratio of 100% in the interval identification. That means your model is not fully consistent with the model is not fully consistent with the verified simulation and the data.
If I can add something else, in this part, we have also some problems of synchronization. We have some timing lag between, because here I did some simulations using DynIbex library under these initial conditions, and we got some results. But in the experimental part, we have some problems to fix these values in the real system. And also, so we have some problems linked to the timing lag and synchronization between the experimental device and the simulation part. And I think because of that, maybe this it affects this percentage, or this percentage of inclusion.
Yes, I fully agree with you. This is one possible reason. But I think there's a second possible reason. Even though that you have done a zero phase filtering, maybe using filt, what could happen again is that you slightly modify also the corresponding magnitude response in a non-favorable way by doing some kind of finite impulse response forward-backward filtering. And I think what could be also compared here is there exist algebraic derivative estimation methods. For example, there's lots of work done by Johann Reger from the University of Ilmenau in Germany. I think he also did it together with Joachim Rudolph from the University of Saarbrücken. And yes, that's one thing that you could do, but you could even do it naively. If you take some successive measurement points, you could try to find some interpolating polynomial. For example, use a Chebyshev ansatz for that purpose, or a Bernstein polynomial ansatz, or maybe even temporal monomials fit in this function, including some guaranteed error bounds that cover the complete horizon of measured data in this time window. And this could be differentiated analytically. And if you take this, maybe you get, again, slightly more robust, because I did this, for example, for estimating parameters also in a similar approach for, it was a quite slow scenario. It was a thermal system. And for that, it really helped to rule out some non-physical behavior.
Okay.
Yes, and the other thing is, what I really like about this graph here is that one sees that, the classical least squares parameter identification is something that is obvious worse because it's for a longer time horizon, fully outside the forecasted interval bounds that you have from the evaluation using this interval-based, the CVR-based identification. And yes, that's something that was also, for example, observed by one of my long-term collaborators from Bernd Tipken, who is since now 20 years professor at the University of Wuppertal. What he did together with a former PhD student was to make a comparison of such subdivision-based, CVR-based identification routines with least squares estimates. And he showed that is quite often very normal that the point valued least squares estimate is something that may be fully outside the solution set that you identify as feasible, especially in cases when the solution sets that you identified with the CVR approach are non-convex.
Okay, understood.
Yes, and this is really a nice scenario where we just see again this phenomenon. Yes, and I have, if I may continue, Tarek, I have one further question. The further question was concerning your online application at the end. Because as far as I understood it, you fully pre-computed the control sequence. And more or less you're applying this pre-computed control sequence to an unstable system. You want to stabilize the pendulum in the upright position with a fully pre-computed control sequence.
Sure.
Yeah, and what you could do there, I think it's even not a bad trick. If you look at your cost function that you did, that's a classical quadratic cost function that you use, for example, also in an LQR design.
Okay.
What you could do is you could modify your system a little bit in such a way that you perform some underlying stabilization using, for example, on the basis of your interval bounds that you designed, some kind of robust, for example, H2 control design, which has a similar behavior like the linear quadratic regulator. What you could do in this case is just over-approximate the system dynamics using some polytropic uncertainty model. At the end, you end up with one point-valued linear state feedback controller for this scenario. This will be running in real time. That keeps you close to this desired behavior. If you compute something like a reference trajectory or feed-forward control strategy, bringing you close to this behavior using your approach. And yes, in such a way, you just perform something like defining a feed-forward control procedure for an already underlying controlled system. And this definitely will help to apply your method in real time on the one hand. And I think it even helps your subdivision-based procedure, because what I think one can see it on the next slide. Because if you have some simulations also performing DynIbex, the bounds will blow up because of two phenomena. One is the uncertainty, And the other one is in the upright position, the system is unstable. And if you're stabilizing the system in an underlying way, it even helps you, I think, finding suitable control procedures. And I think that's not a really bad trick, because in any way, you're already searching for a suboptimal solution. And doing this two-stage procedure, I think, would be a very nice extension.
Okay. Okay. So it's okay. I will try to. I will try to.
Yes, I'm pretty sure that this is working.
Okay.
Thank you, Andreas. Are there other questions, please?
Hi, yes. I have one more question for this page of slides. Yes, the 13. And from your simulation, your identification resource, and we can see that the blue line, the simulated with the interval analysis parameters with the time goes on, and we can see the area of the blue line is becoming wider and wider. I don't know if we can assume that if we simulate it for a much more longer time, this area will become much more longer, much more bigger, or I don't know if this will propose any question for the accurate of the identification results or not.
It's a good question, but actually we didn't try to go further for the simulation part, because this kind of simulation, it takes a lot of time. So for example, to get these results, we wait more than 1 week to get this.
Oh,
it takes a lot of time.
Really time consuming.
Yeah, sure. And I think the way that increase, because maybe the uncertainties, the uncertainties of the dynamic model increases with time. But I think I'm not able to explain this phenomenon because and for me, it's the closures are much bigger here. It means that the uncertainties are much important with time of the state variables.
Okay.
And maybe with time, if we increase the time, I think at 9 seconds, maybe these enclosures will increase with time, I think.
Yeah. So maybe how can we find a point that we can get an accurate estimation resource, and the time consuming, maybe we can, I don't know if we can have some idea for this part.
For the time consuming, I think Julien, because I work with Julien Alexandre this on the réseau. In the end of my postdoc, he recruited a new engineer that he will work in the computation tasks by using by optimizing by using some GPU. We use some efficient computing facilities, and also some parallel computation methods to optimize the algorithms in such a way to attend to reach the real-time domain. But we didn't succeed to follow this part. But I think in the future maybe I will see how to manage this kind of issues.
Yes. Okay. Thank you very much.
Since you just mentioned GPU, that means you already start with a list of sub-intervals to run this blue simulation.
Sorry, I didn't get it. What?
You mentioned that for future work, using the GPU would be reasonable. That means your simulation that you performed here is you really start with a list of sub-intervals representing the parameter domain, and you're running the simulation several thousand of times in order to get your blue result that you depicted here. Sure. Okay. Yes. then I get it. Then using the GPU really makes sense. And yes, that's also some work. If I can also add something, Katja Auer from the University of Applied Sciences in Wismar and myself, we will also have a joint PhD student towards the end of this year who will work also on a similar subject.
Okay, great.
Yeah. No, that's really a promising direction. And maybe concerning Sue's question that you had before, partially this blow up of the blue enclosure could be explained by the wrapping effect of internal analysis. It's partially that you have some box in a multi-dimensional state space that is rotated, and you're enclosing it at the end by, again, maybe something of more simple shape, maybe in the worst case, again, axis parallel. And this may be parts of this blow up. Definitely, Mohamed also decreased this phenomena by splitting the parameter domains. That's definitely a measure to decrease the phenomenon, but definitely also not a measure to fully eliminate it. But what one could try to do here, I think also some perspective for future work, where we could do something also together with Tarek. We could think about including a kind of interval observer in the identification task.
Yes, maybe.
And this could also stabilize the bounding systems then. It's quite challenging in the case because you have oscillatory behavior. That means the corresponding open loop dynamics is not cooperative. But maybe, yes, we could succeed also in finding a solution that here can be interfaced with an identification.
Okay, so the interval observer, what is the purpose of this interval observer? Development of this, the interval observer, it will bring, what is the purpose of this interval observer that we will develop together?
More or less finding in a computational cheap manner a bounding system for the lower and upper bounds of the state trajectories.
Okay. So it's not dedicated to the state estimation in this case. Yes.
No. Yes, you could combine it with your state estimate, with the state estimation, because you already have measurements of all your components of the state vector. This is what you assumed here.
Yes, that's it.
Yes, and maybe one could use, for example, using a intelligent reformulation of the system model, because, for example, shifting parts into like the friction, for example, shifting the friction into something like an unknown input term. One could use an interval observer, for example, to estimate the influence of the partially unknown inputs. And then at the end, again, take the structure that you know, if it's viscous friction, it must be proportional to velocity.
Okay.
We have recently published a paper about NMPC with interval observers for linear parameter varying systems. So there are some ideas which are linked to your work.
Nice. So, and the validation part, it was done with what? For the validation?
On the simulation numerical example. So again, I have a remark about the filter. So as said by Luc and by Andreas, it may introduce a delay, but also it is not robust. The filter of MATLAB is not robust against noises. So even if you use a filter, we can reduce the noise, but you cannot cancel it. So with the filter of MATLAB, maybe the results are not robust and not accurate. So there exist other more efficient numerical differentiator, for example, based on sliding mode techniques, which are very robust, and also some differentiator which are based on high gain observers.
Okay.
What is interesting with these numerical differentiator is that you have you can also compute, you can also have an idea about the bounds of the derivative error. which can be used for the identification process for you. So you can consider more robust differentiator filters.
Filter, okay, in the future, okay.
Yeah.
Wait.
Are there other questions, please, or comments? No?
I think this doesn't seem to be the case. Then maybe it's time now to thank Mohamed again for the interesting presentation, also for answering lots of questions. And yes, definitely we will put also the slides of today on the webpage that you can have a look again also at Mohamed's list of references that he mentioned at the very end of the talk. And for me, it's now time to advertise for the next seminar. The next seminar will be Friday in 2 weeks, given by David Sanders, and he's one of the developers of the Julia interval library. That means we will see some possibilities how to compute with intervals using Julia. And I think maybe he can also give a few words about using the GPU, because he already tested interval arithmetic on the GPU using this library. Yes, and I think that's all for today. Thanks again for attending the seminar. And I wish you now a nice Friday afternoon, evening, and weekend. And we'll see each other again very soon in 2 weeks.
Thank you very much.